Hey everyone, welcome to CafeQED. My name is Peter, and today we are going to be taking a look at the power rule for taking derivatives and also a few of the rules that are usually introduced at the same time as the power rule. So let's get right into it. Starting with the power rule, it says that the derivative with respect to x of the expression x to the n is equal to n times x to the n minus 1, where n is any real number. All right, so let me demonstrate this power rule on a few example problems by itself before we start mixing the other rules into it. So for example, let's say we want to take a derivative with respect to x of the expression x to the fifth power. So this one is a direct application of the power rule, in which case we get 5 times x to the 5 minus 1, right? Because we first move the power down into a coefficient, so we get the 5 out in front, and then we subtract 1 off the power. So then simplifying this, we get 5x to the fourth. Our second example will be to take a derivative with respect to x of the expression root x. All right, so this one doesn't seem like a power rule right away because we don't see the power on the x, right? But remember, let me write this over on the right-hand side. But remember that root x is equal to x to the 1/2. And so knowing that, we can go back and rewrite our problem as taking a derivative of the expression x to the 1/2. Now, in this case, it is the power rule, right? So now we get 1/2 times x to the 1/2 minus 1. And we can simplify this down to 1/2 times x to the negative 1/2. All right, so let's move on. Let's take a look at the other rules that I want to talk about today. The first one will be the constant rule. And the constant rule says the derivative with respect to x of c is equal to 0, where c is any real number. Right, and I think it's pretty straightforward why this one's called the constant rule, because we're taking derivatives of constants. And so just real quick, the derivative with respect to x of, say, 5 is equal to 0. The derivative with respect to x of pi, well, this one might seem kind of weird at first, right? Because we're taking a derivative of another symbol. But remember, this symbol, pi, is just another real number. So it's just a constant, in which case this derivative will also be 0. Okay, so the next rule that I want to look at is the sum and difference rule. And I'm purposely grouping these two rules together because they basically act the same way. And we're going to see why in just a second. So for the sum variation of this rule, we get that the derivative with respect to x of the quantity f of x plus g of x is equal to the derivative with respect to x of f of x plus the derivative with respect to x of g of x. And you could, if you wanted to, rewrite this right-hand side as f prime of x plus g prime of x. But the reason why I'm purposely leaving the derivative operators on these two terms is because I want to make it very obvious that when we're taking a derivative of a sum of two things, we can, or at least it seems like we can, just distribute our derivative into the sum. Okay, so then the difference rule, as you can probably guess, let me just quickly go through it, is derivative of the quantity f of x minus g of x will be equal to the derivative of f of x minus the derivative of g of x. And again, we can rewrite this, if you wanted to, as f prime of x minus g prime of x. And the last thing I want to mention for the sum and difference rule is that even though the rule is introduced as a sum of two terms or a difference of two terms, we can actually mix and match the sum and difference rule on as many terms as we want, and it will still apply. So, for example, if we wanted to take a derivative of, say, the quantity f of x plus g of x minus h of x, this one will just be derivative of f of x plus the derivative of g of x minus the derivative of h of x. So we can apply the sum and difference rule at the same time, like together in one problem, and on as many terms as we want. The final rule is the coefficient rule. And the coefficient rule says that the derivative of c times f of x is equal to c times the derivative of f of x. And again, like before, we can very easily rewrite this final expression as c times f prime of x if we wanted to, but I like to leave it as this form here with the derivative operator because it becomes more obvious that we're basically allowed to move the constant out in front. All right, so now with all four of these rules in mind, let's see them in action on a few example problems. So for our first one, let's consider the function 2x cubed minus 3x squared plus 5. And we want to find the derivative. And so since this is the first time that we're going to be using all the rules together all at once, I'm going to write down every single one of my steps along the way just to make sure everyone can follow along. We get f prime of x is equal to the derivative of the entire right-hand side. So 2x cubed minus 3x squared plus 5. From here, we see that we're taking a derivative of a difference and a sum, which means that we are allowed to distribute our derivative into this bracketed term. So we get the derivative of 2x cubed minus the derivative of 3x squared plus the derivative of 5. All right, so before I start applying derivatives, because some of you might notice already that this final term here we can already evaluate because that's the derivative of a constant, but I'm going to leave it at that and apply all of my derivatives at the very end once I know how to take a derivative of every single term. But as for these two terms, they're not quite power rules yet, right? And the reason is because we still have a coefficient sitting inside, but we do know the coefficient rule, right? And it says that we can pull coefficients out of our derivatives. So we can rewrite this as 2 times the derivative of x cubed, right, pulling the 2 out of the derivative, and then this one as well, minus 3 times the derivative of x squared, and then plus the derivative of 5. So now let's apply the derivative onto each of these terms. So we get, the first term will be 2 times, and the derivative of x cubed will be 3 times x to the 3 minus 1, minus 3 times, and the derivative of x squared will be 2 times x to the 2 minus 1, plus, and the derivative of 5, which is a constant, will be 0. And finally, simplify everything out, we get 6x squared minus 6x. And that will be our derivative. Okay, so let's take a look at another example. So for our second one, let's consider the function f of z is equal to 2 times z to the negative 5 over 7 minus the square root of z plus z to the negative 3. So this one seems a little bit more complicated, but trust me, we know how to take a derivative of this one as well. So the first thing I noticed about this one is this square root term. Right, but remember, we actually saw this a little bit earlier. We saw that in order to take a derivative of the square root, we want to rewrite the square root as a power instead. And the power will be a power of 1/2. So let me go ahead and rewrite my function as 2z to the negative 5 over 7 minus z to the 1/2 plus z to the negative 3. Okay, so now we're ready to take a derivative. So we get that f prime of z is equal to, now because our variable in this function is z as opposed to x, my derivative operator will be d by dz. This is the derivative with respect to z of the quantity 2z to the negative 5 over 7 minus z to the 1/2 plus z to the negative 3. Like before, I see that we're taking a derivative of a difference in the sum, so we can go ahead and distribute that derivative into the brackets. So we get the derivative with respect to z of the first term, so 2 times z to the negative 5 over 7, minus the derivative with respect to z of the second term, z to the 1/2, plus the derivative with respect to z of our last term, z to the negative 3. Then I see that this first term here still has a coefficient in it, so let me go ahead and factor the coefficient out. So we get 2 times the derivative with respect to z of z to the negative 5 over 7. And for the second term, we can actually take the derivative already, right? Because this is a straight up application of the power rule. So let's go ahead and do that. So our second term will become 1/2 times z to the 1/2 minus 1 Okay. And then our third term, same thing. We can apply the power rule already, so let's go ahead and do that as well. So we get negative 3 times z to the negative 3 minus 1. Now, let's apply the power rule again to our first term. So we get 2 times negative 5 over 7 times z to the negative 5 over 7 minus 1. Our second term is going to be minus 1/2 times z to the negative 1/2. And our third term will be minus 3 times z to the negative 4th. And then finally, cleaning everything up just a little bit more, we get negative 10 over 7z to the negative, I think that's 12 over 7. Yep. Minus 1/2 times z to the negative 1/2 minus 3 times z to negative 4. And that will be our derivative for our second example problem. So our last one will be, let's consider the function h of t, which will be t squared plus 1 over t to the 3/4. Then we want to find h prime of t. Okay, so this one looks even weirder than the first two, right? Because I've given us a function that seems rather complicated because of that quotient. And it seems like we're not able to apply any of the rules that we've seen so far. So for some of us who have already taken calculus or maybe have seen more derivative rules, you might look at this and immediately think, oh, this is a quotient rule. I'm going to just apply the quotient rule, and you would be correct. But because we haven't seen that yet, I'm going to try and avoid that for the purpose of this problem. And it turns out avoiding it actually gives us a much simpler way, in my opinion, of approaching this problem. Looking at this, the first thing I notice is that I can actually simplify this function. And how I do that is I'm going to break that fraction up to be t squared over t to the 3 over 4 plus 1 over t to the 3 over 4. And then this I can simplify out to be t to the, what's the top is going to be 5 over 4 plus t to the negative 3 over 4. Okay, from here, notice that now taking a derivative of this function in this form just amounts to two power rules, right? So let's go ahead and apply the derivative now. So h prime of t will be equal to the derivative with respect to t. And this time it's with respect to t because our function is a function of t. Of the quantity t to the 5 over 4 plus t to the negative 3 over 4. Since this is a derivative of a sum, we can distribute the derivative into the sum. So we get the derivative with respect to t of t to the 5 over 4 plus the derivative with respect to t of t to the negative 3 over 4. And finally, we can evaluate our derivatives. So we get the first term will be 5 over 4 times t to the 5 over 4 minus 1. And our second term will be negative 3 over 4 times t to the negative 3 over 4 minus 1. And then simplifying everything out, we get 5 over 4 times t to the 1/4 minus 3 over 4 times t to the negative 7 over 4. And that's our derivative. So again, if you already know how to use the quotient rule, you are more than welcome to approach this problem using the quotient rule without having to simplify first. But because we were able to simplify in this step here, I think that was crucial in allowing us to take fewer steps in solving this problem. All right, so that's all I have for today. If you have any questions, leave a comment below. If you enjoyed this video or found this video helpful, give it a thumbs up. And if you'd like to learn more math with me at CafeQED, hit the subscribe button, and I'll see you all next time.